Consider a solid body rotating about some axis in certain way, let's say anti-clockwise. There are many particles inside the body. Each particle performs circular motion. The radius can change depending on the particle. Radius can be small, it can be large. Just like in case of circular motion of a disk, you can choose a point which is closer to the axis and a point which is further from the axis and apply V equal to R omega for both. Where omega is same for both of them. Why is omega same for both of them? Because both of them have to complete one circle in the same amount of time. In the same time this fellow comes back, this fellow also comes back. Just like that, here also the angular velocity is same for both. In the same time this fellow comes back, this fellow also comes back. Speed depends on radius. Omega is same. Speed depends on the radius. Omega is same. If you have a motorcycle wheel and if you have a scooter wheel and if they have a common axis, this is the axis and that axis is rotating due to the engine. Engine rotates the axis and on the axis wheel is fitted. On the same axis, if you fit a motorcycle wheel and a scooter wheel, axis is the same. That means angular velocity is same, omega is same. In the same time, every particle has to complete one full circle. Whether the particle is closer to the axis or farther from the axis. In the same time, one full revolution. But speeds are different. Motorcycle tire, this particle on motorcycle tire is farther from the center in comparison to this particle on the scooter tire. So what happens is that V is proportional to R. Because omega is same for both, V is proportional to R. That means motorcycle tire, particles on motorcycle tire will run much more quickly than particles on the scooter tire because they are closer to the axis of rotation. In a situation like this, there are so many particles and they are all going at different or same speeds. Particles at the same distance are going at same speed. Particles at different distances are going at different speeds. Speed means v here. But as far as that omega is concerned, it is the same for everybody, because at the same time everybody has to complete 2 pi radians. In the same time, 2 pi radians everybody has to cover. So always remember this point about rotational motion. No matter how the shape of the body is, omega is going to be the same for everybody. And once you focus on any particle, it is just simple circular motion. That's it. It is simple circular motion. Any particle you consider. So once you focus on this particle, simple circular motion. So when we talk about the kinematics, then the kinematics is very simple. It is circular motion for different particles. Of course, different radii are possible. So as far as the motion of a particle is concerned, then the circular motion, all those concepts of circular motion would be applicable. Tangential speed, then tangential acceleration, radial acceleration, all those things that are valid in circular motion would be valid for that particle. We talked about omega as d theta by dt in circular motion also. Here also the same thing, d theta by dt. We talked about alpha angular acceleration as d omega by dt there, circular motion also. Here also the same thing. If you have alpha constant, then we got those 3 equations in circular motion, and if alpha is constant, here also we have those 3 same equations. These 3 are of course valid if alpha is constant. If alpha is not constant, they won't be valid. You will have to go via the calculus route. Other things that we discussed in circular motion, one very important thing was V equal to R omega. Other thing very important was A tangential equal to R alpha. In kinematics, we are not concerned about why something rotates. Just like in simple kinematics and Newton's laws of motion, in case of kinematics, you're not worried that some force was acting and that's how acceleration was taking place. You are just looking at the motion, that's it. So as far as the kinematics part goes, that should be enough. When we talk about dynamics, then the question will come how it is happening, and some additional definitions will come. That's an easy one. Sometimes angular velocity is given in revolution per time. Constant angular deceleration. Alpha is constant. If alpha is constant, you can use those three results. Coming to rest means 0. Suppose I don't convert revolution to angle, but I want to convert time because of this second and minute will be mismatch. Can you calculate this? Unit is automatically coming out to be revolutions. $12.5. 12.5 is the answer I have. Any questions? Let me know. This line is very important. Rope does not slip on the pulley. What it means is this. Particle of rope and particle of pulley, as pulley rotates, then they must have the same speeds. If one is faster than the other, particle of the pulley and particle of the rope, if one is faster than the other, then there could be slipping. So when it says does not slip on the pulley, it means that the speed of the particle of the rope is equal to the tangential velocity, magnitude of tangential velocity of the particle on the surface of the pulley, right? Now for the pulley, for the particle on the surface of the pulley, V equal to R omega. But this particle has the same speed as this bucket, this point, this point, this point. Everybody will go at 20, 20, 20, 20. And so will this fellow be going at 20. And this fellow is in contact with the particle of the pulley and no rubbing is taking place. The particle of the pulley also goes at 20. So this will be 20. So 20, then radius, finding omega should be no problem. Let's find it out. How would you find angular acceleration? Tangential acceleration is equal to R alpha. And bucket has this much of acceleration and no slipping is taking place. So this particle of the pulley also has this much acceleration. Alpha is given, R is given. Well. A tangential is given 4. A tangential is given 4. R is given. Alpha can be found out. Two radians per second and 40 radians per second square. Any questions? If you have, let me know. Here note that it is in centimeter. This is centimeter, this is centimeter, this is meter. So check for any error due to the units. Let me check. If you would like this to be discussed on the board, raise your hand. Any questions, let me know. Then I suppose we can proceed further. V is proportional to the radius if omega is same. So answer to part B should be half of the answer to part A. Yes, 2,1. Unit is meter per second. Any questions? Let me know. If you would like this to be discussed on the board, raise your hand. This is the centripetal acceleration. Acceleration alpha is constant. Radial is 16 centimeter per second square. Tangential is 4 centimeter per second square. If you have any question in any of the steps, let me know. Let me check. 2 meter per second is the correct answer. If you would like this to be discussed on the board, then you can raise your hand. That's your assignment question. Just note it down. We will proceed further. Well, actually there was no need to draw the blades. Just visualize a fan, ceiling fan. In fact, even if it were non-ceiling, it would not matter. The axis of rotation is this. If you look at the center of the fan, assume a uniform fan, not uneven distribution. Obviously, in that case, center of mass must be right here, right? Fan is rotating, let's say, but you would find that center remains exactly at the same position. Whether fan is off or on, moving at whatever speed, that center never changes its position. Center of mass of the fan is not accelerated. And if center of mass is not accelerated, there cannot be any external force. If there is no external force, then why do you need to switch on the fan to rotate it? Before also there was no external force, and now that you have switched on and the fan is rotating, even now there is no external force because the center of mass is not accelerating. Then why do you need to apply any switch, Why do you have to switch it on? The answer is that force alone is not enough to discuss rotation. Force alone is not enough to discuss rotation. If you have played with screwdrivers or at least have watched mechanics using screwdrivers, then you must be possibly aware, you possibly may be aware that longer screwdriver is easier than a short screwdriver, short versus long. If you have to open some screw, longer one is more convenient. I'm not talking about very easy to open screws, but somewhat harder. Let's say car tire is punctured and you need to open it up. Now you can take that thing which is very small and try to open it using that. You can take it long and then try to open it. Long one will be easier. Even if you apply equal force in both cases, short versus long, equal force you apply, you find it opens more readily when you are using the long tool. Force is not the only thing. So we need to define something which is just not force but is beyond force. Distance is a very important thing that I just mentioned to you. Long screwdriver. How far the force is applied? That thing is very important in rotation. How far the force is applied. So we define a parameter which takes care of force and distance both. Force and distance both. And that is called torque. Torque is defined as R cross F. Say for example, this is the point of application. In fact, let me say this is the point of application. P is the point of application. Point of application of what? Force. Torque is about a point. Torque is about some point, not necessarily the point of application. Torque is about some point. Point of application is P, somewhere else. We are finding torque about point O. Then if O is the origin, then vector R is the position vector of point P. Vector R is the position vector of point P. So torque of the force F acting at point P about point O is given by R cross F. That's the definition of torque about a point. Often we are interested in the axis of rotation. Fan is rotating about some axis, solid object is rotating about axis, wheel is rotating about axis. So often we are interested about axis. So we need to extend this definition to torque about a line. Right? Torque about a line will require some explanation. So that we will continue. In the next class, And we stop at this point.